is Jacob Washburn, and today's date is February 3rd. I'm going to be giving a speech on Moore's Law and how it's failing. And during my speech, I will have 3 points. My first point will be talking about Moore's Law, what it is exactly, why it's failing. Then I will move on to Dennard scaling, which what it is and how it's linked together with Moore's Law. And then I'll move on to multi-core and super scaling, which is what is happening today, and the effect that Amdahl's law has on those two things. Oh, and my audience members are Shayla Robinson and Noah Wall. Right. According to Britannica.com, in 1965, Gordon Moore, the director of the Fairchild Semiconductor Corporation, coined the term Moore's Law, that the number of transistors in an area doubles every 18 to 24 months. What that means is that on a chip of the same area, we can put double the amount of transistors in that area. So basically double the performance or power. What a transistor is, also according to Britannica.com, is a semiconductor device for amplifying, controlling, and generating electrical signals. Transistors are basically what make the hardware side of computers run. They transfer all the signals, they turn on and off, and that does, based on whatever the code is, does a certain thing based on, what was written already. To give you kind of a view of it, since I don't have a presentation or a picture, for the degradation of Moore's Law over the years is, in 1978, around the time, a few years after the law was termed or coined, from about 1978 to 1986, there was a 25% increase in single processor performance. That's important for later in the speech when I talk about multi-core. From 87 to 2003, there was a 52% increase in PC performance, which is basically the heyday of Moore's Law, right? That's when we started to see a really big decline. Because from 2004 to 2011, there was a 23% increase. From 2012 to 2015, a 12% increase. And then from 2016 to 2018, only a 3.5% increase. So the amount of performance that we're getting is reaching the law of diminishing returns, which basically states that after a certain point, it doesn't matter how many more transistors you add, you will not see as much of a gain in the performance. On to Dennard scaling. What is Dennard scaling? According to the book, Computer Architecture, A Quantitative Approach, Robert H. Dennard observed that power density was a constant for a given area of silicon, even as you increase the number of transistors. So, Moore's Law, right? Dennard scaling and Moore's Law walk hand in hand. When one fails, the other also fails. Because, I guess let me explain Dennard scaling. Essentially, the same amount of power density regardless of the transistors in the area will be applied. So even if you double the number of transistors, the same amount of power will be applied. Now that sounds great, and it sounds like it should never ever go away. But also according to my book, The Computer Architecture Quantitative Approach, it was Understanding Dennard Scaling from Ramos.com. And it was, with features, sizes, which is transistors, below 65 nanometers, the rules would no longer be sustained because of exponential growth and leakage current. Now what that means is in computing, there's 3 different types of current. There's active, there's, I'm forgetting what it's called, but it's basically when something's in use, and then there's leakage. Leakage is all the time and cannot be taken away. You can never not have leakage current. Just like when your phone's in use, you're using active power, but whenever it's not in use, it's still losing power through leakage. Now, since the number of transistors as it increases and the power increases, the leakage current goes up exponentially, so you start losing an insane amount of power to the leakage current. And this is the actual reason why Moore's Law is failing. We have violated Dennard scaling, and we did that 10 years ago. But as far as where we're going, there's 2-ish different ways that are pretty prevalent, and it's multi-core, which is you see everywhere with the quad core and the 16 cores on everything, and it's just getting more and more. They're trying to use Moore's Law in terms of cores. But basically what they're trying to do is they're trying to split code between different cores. And when they do that, they can speed it up by saying, okay, I'm going to take half the program here and put it over here and half over here and do them at the same time and get twice the speed. Problem with that is that Amdahl's law comes into play, which this is from the same book, Computer Architecture Quantitative Approach. But Amdahl's law states that the specific performance improvement to be gained from using some faster mode of execution is limited by the fraction of time the faster mode can be used, which basically means that if 50% of the time you can use the faster code, then that will be proportional to the amount of speed up that you get. So if you could use it more often, then you would get a better speed up, right? So if it was 75% of the time or 90% of the time, 90% of your code. And then the other side is superscalar, which basically breaks code into different, you take different instructions and you bring them all in at once. So you can do more instructions at one time than you could with the single processor. So you just focus on pushing as many instructions through as possible. But it also suffers from Amdahl's law because of if you have code that's not parallelizable, which means it can be run in parallel to different areas, then that's the part of Amdahl's law that limits it. And that's it.